characterizing low-mass cold exoplanets with the Nancy Grace
Attention, please.
Thank you.
Thank you for the introduction. Hello, everyone. Hopefully your lunch was great. Happy Friday also. I'm Sean from a postdoc from UMD and Goddard. Today I'll talk about the Roman Space Telescope and how Roman will deliver quite a lot of exoplanets from the microlensing detection technique and also transits. So first, the namesake of the Roman mission comes from Nancy Grace Roman. She was the first chief of astronomy at NASA in the 60s. Here she is on the right, photo from the 60s with a preliminary design of what would later become the Hubble telescope. So she's very instrumental in pioneering space-based observatories. So she's often called the mother of Hubble. The left is a mock design of the Roman telescope, which is being integrated and built at the high bay, the clean room at Goddard. So many of you might be familiar with this animation. I like it a lot. It shows sort of a top-down view of the Milky Way and different detection techniques for exoplanets as a function of year. So we see this zoom in around our local neighborhood. Many, starting in the 90s, many radial velocity planets. You can see the big boom from Kepler for transiting planets. But the green data points, I'll just pause it at 2021. The green data points come from the microlensing detection technique. And one of my favorite things about the microlensing method is that it really probes this very large range of distances to planetary systems that some of the other techniques can't do at the moment. So it really gives you kind of a galactic distribution or an idea of understanding of the galactic population of exoplanet systems all the way to the center of the galaxy. So I have one quick slide on microlensing, so I'll kind of speed run this slide. I don't have enough time, but microlensing, the phenomenon requires a very precise alignment of three sort of references. One is the observer, or a telescope. The second is a foreground object, or what we call the lens. The third is a background star called the source. So if these three come into a near perfect alignment, the gravity of the foreground lens can bend the light coming from the background source and to create multiple images of the background source star. Typically, our telescopes don't resolve the multiple images, and what's actually measured is just this overall brightening and dimming of this light curve in this inset panel, of brightness over time. Here's a real example of the first published exoplanet from microlensing. The top panel shows real telescope data. Conveniently, there's a circle to train your eyes to what's happening in the middle there. There's a pretty unique brightening happening in this microlensing event. The light curve on the bottom is just tracing the real photometry, the photometric data that was taken. There's some sharp, interesting features. The real light curve and this toy model one on the left look very different. The real event is a binary lens, so it has a star and a Jupiter mass planet. I like to think all sort of binary lens microlensing events are unique in their own way. Their light curves could look very different. These sharp features are due to something called caustic crossings, which I don't have time to get into, but that is my speed run of the microlensing slide. Back to the Roman survey that I'm going to talk about. So there's a few core community surveys that will be conducted on Roman, with Roman. One is the Galactic Bulge Time Domain Survey, or GBTDS. And as part of that, the Roman Galactic Exoplanet Survey will be conducted. So we're now 2 layers deep in the NASA acronym land. So the ARGIS will be conducted. Here's an animation I really liked Robbie Wilson made at Goddard, showing one realization of the observing strategy for this GBTDS. I'll stress it's not, very likely not the final, and these numbers are not the final, observing parameters, but it'll sort of tile through these 7 or so fields and sort of integrate over this loop every 15 minutes. So the cadence will be 15 minutes, 50-second exposures, 6 seasons. So by the end of this survey, it'll effectively be one of the deepest exposures ever taken of the sky in this region. And again, just stressing one more time, These numbers are not final. There's actually several survey definition committees that are convening right now to deliver their final recommendations for these surveys. I believe by the end of this year is when they're tasked with delivering, or maybe spring 25. This plot's been, I'm sure a lot of people are familiar with a figure like this, but these are generally the expected yields for the microlensing survey on Roman, orbital distance versus planet mass. So about 1,400 or more bound planets, 300 or more free-floating planets, and 50 or so isolated black holes and neutron stars and other compact objects. So free-floating planets and black holes don't really have a nice place on a plot like this, but I just kind of drew arrows pointing to where they would live. Free-floating planets, of course, don't have a semi-major axis. They'd be off to the right, compact objects off to the top right. This is a sort of updated version of that figure. Transiting planets, the yield is expected to be huge for Roman. I don't have, this talk is about microlensing, but for anyone very interested in the transiting exoplanet yield, there's a nice study done by Robbie Wilson again. So I would recommend reading that paper about the expected transiting exoplanet yield, potentially 100,000 or so transiting exoplanets, mostly giants. All right, I have to speed up a bit. So back to microlensing, some light curve observables, so things that you measure through a light curve. I just put up another example of one measured from 2009. I'll focus on this observable this quantity called the mass ratio, or Q, planet to star mass ratio. So I think of this as sort of an unphysical quantity. You don't actually get the mass of the host and the mass of the star from this. Of course, you just get a ratio. So typically what historical microlensing discovery papers will do is in their analysis, their Bayesian analysis, they'll assume a prior distribution on the planet hosting probability, which basically says the stars of any mass are equally likely to host a planet of the given mass ratio Q. So this turns out not to be such a great assumption to make. But how can we get a true mass for the host itself and the planet that's orbiting it? There's these things called higher order effects that can be measured in the light curve for microlensing events. Some of them are microlensing parallax, pi e, finite source effects, which give this theta e parameter, the angular Einstein ring radius for the lens system. And there's actually a third relation that comes from directly measuring flux coming from the lens star itself, if it is a star, if it's luminous. And so I'll note that to get a true mass of the host and the planet, and not just a Q mass ratio, you need some combination of two of these three. So I made a quick animation just demonstrating. I'll talk about the third one, so measuring flux coming from the lens. So I take just a high-resolution image of some field near the center of the galaxy, two stars, and I go into simulation land. And many years before the microlensing event, these two stars, a source and lens, have relative proper motions. Maybe they're wobbling from parallax. They're doing a bunch of different things, but everything's moving relative to each other. At 0 years, you have a microlensing event, and some years later, the stars begin to separate on the sky. And so we can take high-resolution images and try and directly detect the lens star itself after the microlensing event. This equally works in reverse. So actually, precursor or serendipitous high-resolution images before a microlensing event can also hope to detect the lens. We have a few more minutes left. So there's a few scenarios in this case where you're trying to detect light coming from the lens, the host star. Fully resolved scenario is kind of the most straightforward. Here's one paper that a member of our group, led by Dave Bennett out of Goddard, Katie Vandero, postdoc in our group, worked on this event. So the event happened in 2013. And this is Keck data from 2019, I believe. And so clearly many years after the event, the lens and source have separated from each other. You can use your favorite PSF fitting routine and just fit and get astrometry and photometry directly of the lens host. Moving a bit higher blended scenario, we call it image elongation scenario. So this is before they fully separated the source and lens. This is another event from HST data, Aparna Bhattacharya, another group member at Goddard, worked on. So the lens and the source here are more highly blended, but you can still fit a single PSF model. You get this very classical residual, this signal that's kind of a dipole in the residual image that is indicative of a blended, 2-point sources very close together. Yeah, and fitting 2 PSFs gets a much smoother residual. So Roman will, use this method as well as the other 2 of those 3 methods to get true masses of hosts and their planets. So from that, particularly this lens flux measurement, you can use something like an empirical mass luminosity relation or a stellar isochrones or things like that to actually get a mass and distance relation for your lens system. So these are sort of how we expect to further characterize these planetary systems through their masses. And distances are also very important, of course, how far away these systems are. So here's just one more example in a mass distance space for a target. The red curve shows the Keck measurement. The green is, again, one of these other finite source effect constraints. And so with the total mass of the system and Q that you get, the mass ratio, it's pretty straightforward to get the individual masses. That was with 2 of these 3 relations solved. Here's with 3 out of the 3, so it's just a more robust measurement. And again, Roman will use all of these methods to get some number of planets. So I'm out of time. I'll leave up my summary and just make one last important note that actually there's a requirement set by NASA on these microlensing host stars and their planets that at least 40% of the hosts should have a mass measurement. So solving these relations to a precision of 20% or better. With that, I'm happy to take questions. Thanks.
All right, thank you, Sean. Very interesting talk. Any questions from the audience?
Hi, Susan Lally, Space Telescope Science Institute. Maybe I missed this. How long do we have to wait to get all these mass measurements kind of on average? I know it's a distribution, I'm sure, but am I waiting 3 years, 10 years?
Yeah, good question. The 2 scenarios that I showed require a little bit more time, several years. I would say it actually depends on the distribution of the relative proper motions. So for a disk, a lens in the disk, and a source star in the bulge, sort of the average is between maybe 3 and 5 milliarc seconds per year, the relative proper motion. So in a Roman pixel is something maybe like 100 milliarc seconds. So it'd be a fraction of a pixel in just maybe a year or something, but Roman will be 5-ish years long. I didn't show the most highly blended scenario, which actually uses this color-dependent shift of the centroid of the star, which is can even achieve much smaller differences that Roman can employ as well to get those mass measurements.
Okay, any other questions?
I have a question. How ready are you for the amount of data that Raman wide field instrument is going to generate? Like, is it overwhelming? Like, or like, let's say, like your actual codes to look for microlensing events, do they apply to like multi-chips and all this data that's going to come?
Yeah, I think it used to be more daunting than it is now. I think I don't have too much information about it. I know that sort of there's a pipeline being worked on and developed by IPAC for Roman data, and so it's going to. I think they're implementing sort of AWS services and these sort of technologies to handle and mitigate terabytes and terabytes of downstream data. Okay. So it's not unachievable. It's not impossible. It'll be handled sufficiently. Yeah.
Okay. Thank you, Sean. Let's thank Sean one more time.
Yep.
And our next speaker is Keelan Hoch, and she is a Giacconi Fellow at STSI, and we will learn more about special characterization of the YSES-1 multiplanetary system with JWST.
Awesome. Okay, everyone can hear me? Awesome. Hi, everyone. Thank you guys so much for being here today, and thank you for the conference. Thank you to the conference organizers for making all of this happen. So I'm going to talk with you guys today about my CHEXO11 program to spectrally characterize the multiplanetary system, YSYS-1, which is the shorter version of the name. So I just wanted to take a quick second to recognize our team. So I'll be talking and highlighting some work done by the people in blue on the team, but people in orange were very imperative for reducing all of the data, which has taken a very long time, seeing as this data was taken in cycle 1. So just to put this program into context, we have our famous plot with mass versus separation, with all the different detection methods sensitive to specific populations here. But one interesting thing about this plot in particular is the fact that everything with a little outline around it are planets that have spectra, actual measurements of their spectra. So the only methods that can currently do this are direct imaging and the transit method. But JWST high contrast imaging spectroscopy has actually started to expand this parameter space not only into the 3+ micron range wavelength, but also starting to push to higher and higher contrast to lower mass objects. So we're really excited to see what JWST is going to show us about some of these wide orbit objects. So direct imaging and moderate resolution spectroscopy are notoriously difficult from the ground past 3 microns. But we have been able to do some really exciting work from the ground. So the plot shown to the left is Konopecki et al. 2013. This is showing spectra from HR8799c with different spectral templates of the different molecules that were detected in the atmosphere. The bottom panel is going to be the cross-correlation function, which is the detection of each of these molecules. To the right are going to be the HR8799 planets from 3+ microns from the ground. They're still amazing spectra, but again, doing the same type of molecular mapping or cross-correlation is just not applicable here. But then in comes JWST. We have this amazing spectra that I think we've all seen before of VHS 1256b, where we 1256b, yep, where we have full spectral coverage from 1 to almost to 15 microns, even past 15 microns. We've detected silicus, we've detected carbon dioxide, carbon monoxide, methane, all of these amazing features. But the interesting thing is that this system is fairly low contrast. So the planet, or brown dwarf, about 13 Jupiter masses, is around a binary system, but there's no need for any post-processing here because the starlight was so faint. The host starlight was so faint. So introducing our system for cycle 1, we wanted to get complete spectral coverage from 1 to 12 microns of this multi-planet system, YSYS-1. So this is the first directly imaged multi-planet system around a sun-like star. It was discovered in 2020, which conveniently was after the ERS teams had gobbled up all of the interesting targets. So we were able to play around with this. We also found out that both companions were able to be put in the same field of view with the near-spec IFU. So it's kind of a 2 for the price of 1 ordeal. But one of the other reasons why this planetary system is so interesting is that the host star is 15 million years old. For context, that's fairly young. The inner planet B, closer to the host star, is about 14 Jupiter masses. The planet further away is about 6 Jupiter masses. So this system is interesting because we can look at the spectra and compare the atmospheres to each other, thinking that these planets probably formed in the same formation environment. So shown to the right are the ETC calculated kind of simulated data cubes of what we hoped to happen with the near-spec IFU. This is what did happen. So it was fairly decent, but the pointing was off just slightly. So C ended up on the edge of the field of view for 2 of the dithers. So we hope to see if we can recover C from these 2 dithers in the future. But so far, for the analysis coming up, we've only used 2 of the dithers with C that's actually in the field of view. We also have Miri-LRS spectra of the companions because not only did we want to look at the composition and chemistry of the 2 objects, we also wanted to see what the cloud composition was for B and C. So we nailed it. We got B and C in the slit for Miri-LRS. So looking into our near-spec IFU data, I'll play this. So you can clearly see the 2 companions. I have them circled here. And we're moving through the wavelength axis because this is our IFU data cube here. This is before the outlier rejection was improved in the NearSpec IFU pipeline, but this is our combined data cube with the two dithers of our two companions. So the starlight is clearly contaminating both companions, B significantly more. So in order to get the spectra from the two companions, we need to remove some of the starlight. So let's go here, awesome. So we don't have a reference star image for our companions here, so we actually used WebPSF to model the starlight of the host star and subtract it out. So these are just stepping through the different wavelengths of the data cube, kind of showing how we created the WebPSF model data cube that we eventually subtracted from the data. If you look in the bottom panel, though, there is some weird little circle there that is not real. That is from saturating the NearSpec IFU, which high contrast people will do a lot. So, oops. We had to do the same thing with MIRI, though, right? Because these companions still have starlight contaminating them. Thank you. And you can see kind of the speckles and the kind of fuzziness that's happening next to both companions, B significantly more. So we also used WebPSF modeling to model the host starlight within the slit, and we're doing a fairly decent job at removing most of the starlight. So I'll show you some spectra here. So this is from the ground. So again, this is YSC. This is the 6th Jupiter mass exoplanet orbiting our sun-like star. So you can see here, these are the photometric points that we could get from the ground. Next, I'm going to show you the PRISM data. So this is from 1 to 5 microns. It's beautiful data. The error bars are plotted on there. And then here are some of the spectral features we see just in the PRISM data. So we see methane, we see CO2, we see CO, some amazing molecules that are really indicative that this atmosphere is in non-equilibrium. Now, the exciting part is going to be our MIRI LRS spectrum. So the error bars are also plotted here, but you see this feature around 8 to 10 microns is the first detection of silicate clouds in an exoplanet around a sun-like star. So it's absolutely incredible. We saw it in VHS, but this is a similar feature. We're still trying to figure out exactly what silicates are made of for this object, but it's super exciting to be able to see this. So trying to model this with non-equilibrium chemistry and clouds, it's notoriously difficult, and it doesn't fit very well. And this is our best fit model currently. Now, we are just using forward models, no retrievals yet. But no, don't fear. Melanie Rowland at UT Austin, who's a grad student, is working on creating models for the silicate cloud features. So moving on to B, we also have the full wavelength range for B as well. So here's what it looked like from the ground with photometric points. And here's our PRISM spectra. And then we also have the same thing. We have our MIRI spectrum. So one interesting thing about the MIRI spectrum here is that it doesn't go back down. Kind of goes up and then flattens out. And we weren't really sure what could be causing this. So if you kind of put a model on it and try to model the data the best you can see that most models want to go down in that wavelength range. So we believe that this is evidence for a circumplanetary disk around B, so that's the inner planet. So we have Carl Ingebretsen, who is here, a JHU grad student, who is going to be working on modeling this disk, figuring out what it's composed of, and also just in general, what's going on. So using forward model grids, a lot of these models are struggling because this is a wavelength range we've really never experienced before with exoplanets. And some people may ask, are you going to run retrievals? Yes. So Eileen Gonzalez is going to be leading the retrieval analysis for the entire spectral coverage that we have. We also have high-resolution data that are still coming. So I'll end here, trying to end on time. So JWST is actually opening up a lot of new questions. So a lot of these substellar atmospheres are going to be in non-equilibrium chemistry. So that means we really need to update our atmospheric models to include this. We're also seeing direct detections of silicate clouds for the first time in these atmospheres. Where did they come from? How did they get there? How do we incorporate them in our models? Are they going to keep messing with us? So again, what are the origins of those? Is there something feeding the circumplanetary disk in this system in particular? Or did it come from formation? Did it hold on? And then what will the high-resolution data reveal? But all in all, JWST, MIRI, and NearSpec are going to be instrumental in showing and trying to answer some of these questions and then opening up new ones. So thank you all.
Thank you so much, Keelan. This is great. What nice spectra you get from JWST. Okay, any questions from the audience?
I don't know. Same time. I think you were at the same time.
I think Eric was first.
Thank you. Eric Lopez, NASA Goddard. I'm really intrigued by this mysterious infrared excess that you were just showing. I was wondering,
Me too.
in addition, does it have to be a circumplanetary disk? Could you maybe instead explain it with a large moon, large exomoon?
That's Laurent's favorite thing. He really believes in moons. I've not tried moons, so obviously we didn't expect to have this infrared access, so we can try it, but I have to find some modelers to help out with that. Currently, the best model we have is like a double disk or something, but there's still some weird emission going on, so that's hopefully something that Carl will answer.
Okay. I have seen people suggest looking for exomoons with this sort of infrared excess, so.
Well, send them my way.
Yeah.
I just have giant question marks over here, so bring me your ideas.
All right, next question is from, I think, Zafar.
Hey.
What's up, Safar?
How you doing? Wonderful spectra. Those are some of the most beautiful spectra I've ever seen. My question is,
thank you.
how much do you trust the absolute flux calibration between visits and acquisitions such that you can do time variability studies?
That's a good question. Between visits of just like observing the object, I'm not entirely sure. Nile has a program, I think, that's doing something like that.
I think you can, the jitter, the residual jitter of JWST is about 3 milliarc second or even
Yeah.
less, 1 milliarc second. So there's no reason why you cannot stare at this.
Yeah. Flux calibration is an ongoing discussion, though.
Okay, any other questions? I have one.
Oh, yeah. What's up?
So is persistence a problem in this kind of observations?
What do you mean?
Like when you observe one object for a long time, do you have any instrumental effects in the detector that can, for instance, influence your results?
I mean, there's going to be detector systematics. Hey, Elena, you can put your thing up if you want to. Yeah, so the detector effects have been kind of a nuisance, I think, in general for some of these observations, because there's a lot of things that we didn't expect when we were testing all the instruments or when other people were testing instruments from the ground. We didn't stare at the objects too long. It was a small program, so I'm not sure, the length of time and looking at some stuff, but we've definitely found obviously like the ghost that was in our data. We have the wiggles in the data cubes that we have to try and mitigate. But other than that, there's not really much I've found with like this data set in particular.
Thank you so much. All right, so let's move with our next talk, and that's delivered by Elena Manjavakas, who is here at STSI at the NIRSPEC team, and she will be talking more about young brown dwarfs. So take it, Elena.
Can you all hear me? All right. So today we are not going to talk about planets anymore. No, just kidding. I'm going to show you guys how the first spectra of NIRSPEC JWST of very young brown dwarfs look like. First, to keep everybody on the same page, I'm going to explain what brown dwarfs are. And this is for, before the times of the internet, about 20 years ago, 25 years ago, we knew all kinds of stars, being like the least massive stars, M dwarfs. And in our solar system, we knew giant planets being the most massive planet, Jupiter. But there was a gap in between in terms of masses of objects that we knew that was not filled in. That's where brown dwarfs came into play. And these were discovered in 1995, same year than the first exoplanet. And with the advantage that brown dwarfs, as planets do, they do not burn hydrogen. but brown dwarfs are usually isolated, so they are so much easier to observe than exoplanets. So all you guys are gonna be so jealous about the spectra I'm gonna show here. Just a spoiler alert. So up to now, we know about like 3,000 brown dwarfs, and as stars in a sense, they do have their own spectral types. They have masses between 80 and 13 Jupiter masses, and as I mentioned, they have 3 spectral types, L, T, and Y, being the least, like the coldest brown dwarf we know, 250 Kelvin, so not that far from Jupiter. If we put all the brown dwarfs in a color magnitude diagram, dwarfs over here, like the orange zone that we have here, and here are the T dwarfs, which, as unexpected back in the day, they are bluer but colder than L dwarfs. And what happens in what is called the L3 transition is a very interesting thing, and is that unexpectedly, and this took a lot to explain for brown dwarf modelers, is that clouds that are in L dwarf's atmosphere sink below the photosphere and transition to T dwarfs. Yeah, brown dwarfs, actually I was talking with someone about this. Brown dwarfs change spectral types along their lives because they cool down. They have no source of energy inside. So they change spectral types, and when they cool down below about 1,100 Kelvin, the cloud sinks below the photosphere, and also chemistry goes on. Basically, L dwarfs are dominated by CO, and that CO transitions into methane. So the way you know you are finding something, you are finding a T dwarf, is because the T dwarf has methane in contrast with L dwarfs. Keep that in mind, because that's going to be important for what I'm going to show at the end. And if you are wondering what is happening at the very bottom of it, is that that part of the color magnitude diagram is where we find the TY transition, and that part of the diagram is going to be very populated now by some white dwarfs that have been observed by JWST, and for which we have amazing spectra as well. Which are the brown dwarfs that I did observe? Well, the very first thing you need to keep in mind is that this is an age benchmark sample. Given brown dwarfs, again, indifferent with stars, given a brown dwarf, we don't have any idea of what's the age or the mass of a brown dwarf, because there is no main sequence. So the only way we can have an estimation of the age of brown dwarfs is if they belong to a young moving group or an open cluster or something like that. So in this sample, we were very lucky because we got 3 members of the TW Hydra Association, which is 10 million years old. So it's also very young, as Kilamon said, this is very young. And we have 3 objects. So TW28, which is an M9 brown dwarf, about 21 Jupiter masses, has a disk. This one has been already studied from the ground. The same for TW27E, similar spectral type, similar mass. And 27A has a companion, 27B, which is also very well known as 2mass 1207B. And this is about L6 spectral type, and also very low surface gravity. This was the first directly imaged exoplanet back in the day. And it has a mass, this is very well known, about 5 Jupiter masses. And there is before, what I'm going to show here is like if this object might also have a disk. This was done with ALMA data before the times of JWST. And if it does have a disk, the mass of the disk was estimating upper limit of a mass of the moon. So we took JWST data using the IFU and NIRSPEC on the highest resolution end, covering all the wavelengths from 0.97 to 5.3 microns. So we got a very high resolution, high wavelength coverage spectrum. And this is how the spectra look like. So the very first time I plotted them, I must say I was like, all right, they look pretty nice, but I was not super impressed. And then I decided, okay, I'm gonna see what I can find, which spectral features I can find here. Do I find more data from the ground, or what do I find? So I plot everything I knew. And then I realized that most of these wiggles are some species. Of course, you see the potassium lines, the alkaline lines that are always there and are very prominent, but you also see some little lines that I have never seen from the spectra, in the spectra from the ground. I want to draw your attention because in the very bottom, in the blue, the clear blue, sky blue, you have the spectra of TW27b, and you see that there is one emission there, one emission line there, patient alpha, there is helium, and there is patient delta as well. And we're talking about a 5 Jupiter mass object that is showing emission lines which come most likely from a disk, basically, from the accretion of the disk. That's the only explanation you can find. So that's the first discovery. Yay, this 5 Jupiter mass planet has a disk. And if you go to the next part of the spectrum, there is another very big patient beta emission line. And in the next part of the spectrum, there is a patient alpha emission line. So this spectrum of this planet is full of emission lines. But then, of course, what we wanted to do is not only, okay, we have very cool spectra, but do the models do a good job on reproducing the spectra of this object, particularly 27b. But in the paper, where you can check actually in the QR code that I'm going to leave at the end, I have the other two objects that I compare to models and everything. Of course, the most interesting results were for the planet. So I compare all the spectra to models, to the BTZ atmospheric models that are cloudly models that include disequilibrium chemistry, and also to the atmospheric models. Those are cloudless models, and they have also disequilibrium chemistry. So basically, you can check the paper for the thorough comparison that I did to all the models, but I'm just going to highlight the most interesting point that I found. This is the spectra 27b, so of the planet. And overplot, you have the ATMO best match and the BTZL best match. And you can see that here we are expecting a methane feature because this is an L6 object. So it's getting very close. It's starting in the LT transition. So it should be starting to show some methane. And that's what the model predicts, both cloudly and cloudless. But actually, in the spectra, that methane feature is not there. And the same for the CO. So the models predict very prominent CO features, but the spectra doesn't show any CO features. And what is even more interesting, because you could say, oh, both models are wrong, right? But if you actually compare to other spectra of similar spectral type, but older, so at the top we have TW27b, in the middle we have PSO318, which is 27 million year old, and at the bottom we have VHS 1256b, which is 140 million years old. The other two spectra do show the methane feature, and VHS also shows a very prominent carbon monoxide feature that we don't see in the spectra of the planet. So why is that the case? What is going on? Well, it's the first spectra of such a young Rondorf/planet of this spectral type that is that young. There are not many examples of this super young spectra of the L3 transition Rondorf because they are very faint. Usually they are pretty faint. So we have to keep searching. So in conclusion, in this neurospec spectra, we find all the atomic and molecular bands that are expected for young brown dwarfs. I encourage you to go to the paper and look at them because they are amazing. WA27b shows emission features pointing to the existence of a protoplanetary disk. Atmospheric models reproduce the spectra of the two brown dwarfs pretty well, but not of the planet. And actually, atmospheric models overpredict methane. And the reason what I believe this might be happening is that because it's a young object, has low surface gravity, and one of the explanations that could explain why we don't see any methane is that the L3 transition is actually delayed for very young brown dwarfs or planets, call them the one you prefer, due to the low surface gravity. Of course, this is the only one we have. So we need basically to populate the color magnitude diagram that I showed before also a low surface gravity and see if this LT transition is actually delayed or for some reason this object is just special. So if you want, that's the QR code for the paper that was published a few weeks ago. And you can download the data from the paper and do all your retrievals and have fun with it. Thank you.
Very impressive. Thank you, Elena. Questions from the audience? Zafar?
Wonderful talk and beautiful spectra. I was wondering, do the relative strengths of the passion lines tell you anything about the temperature or the conditions of the accretion? And then separately, what is your thinking about why the CH4 is depleted in PWA27b?
Right. So actually the width of the emission lines actually tell you about the accretion rate. So Kevin Luhmann, before I published my paper, he also has a paper only about that object, and in that paper he actually did analysis of those lines and has like the accretion rates that are predicted on those lines. And yeah, as I said, the depletion of the methane, I believe is done because basically the LT transition is delayed, right, due to like the low surface gravity. So that's what I believe it can be happening. But again, we need to populate this plot with more objects. Actually, Keelan object might be a good one to put in compare to see if if it happens in other objects too, or it's just special, or it's just an artifact.
Cool. And are there lithium abundances for these objects?
The what?
Lithium abundances?
We don't have lithium abundances because, well, the lithium, we can measure it only in the optical. And yeah, we don't have optical data.
Thank you.
All right. Any other questions? Okay. No more questions. Thank you so much, Elena. Okay, and our final speaker is Matthew Nixon from the University of Maryland, who is going to tell us more about the internal structure of GJ1214b.
All right. Is this on? People here? Yeah? Okay. By mistake. That would be a fun challenge. Do it for the flash dogs. All right. Does this work to go back and forth? Nice. All right. Hi, everyone. Thanks so much for organizing this event and for coming here to listen to me today. So I'm going to be talking about the internal structure of GJ1214b. And some work that I've been doing in collaboration with all of these folks listed here. But first of all, why do we care about GJ1214b in the first place? Why is this an interesting target? So I imagine many of you already know that GJ1214b was one of the first sub-Neptune exoplanets to be discovered back in 2000. And so its very discovery and the subsequent discovery of a ton of other sub-Neptunes raises a lot of really fundamental questions about planetary systems, right? We don't have any planets like this in the solar system, and so we don't necessarily know what these things are, whether they're scaled up versions of rocky planets or scaled down ice giants or something else entirely. And GJ1214b throughout this time has remained one of the most favorable sub-Neptunes in principle for further characterization of its atmosphere through spectroscopy, thanks to a favorable planet-to-star radius ratio and a bright host star. So for this reason, it's been pretty extensively observed from ground-based instruments and also using the Hubble Space Telescope. But it's turned out to be a little bit more challenging than we maybe would have thought at first. So here I'm showing the infamously flat transmission spectrum of the planet observed using Hubble's Wide Field Camera 3. And so normally transiting exoplanet people get really sad when they see a flat line. But in this case, this is still tricky. You can't necessarily infer a unique composition for this planet because of the flat transmission spectrum. But in fact, this thing is so flat and so precise that we did learn something from this transmission spectrum. Even a high metallicity atmosphere, a high molecular weight atmosphere, is too bumpy to fit the spectrum, which means that you need some kinds of aerosols, some kinds of clouds or hazes in the upper atmosphere in order to explain these observations. So we did learn something about the atmosphere from all of this. However, unfortunately, you aren't able to learn very much about the composition due to those clouds and hazes in the upper atmosphere using HST. But of course now we have JWST, we have much greater observing power, and maybe it's an interesting question to ask whether JWST can teach us any more about the atmosphere of this planet. And thankfully the Cycle 1 TAC agreed that this is an interesting question, so they dedicated time for a full phase curve of the planet to be observed using MIRI LRS. And so here I'm just showing the white light phase curve. You can see the transit in the middle and 2 eclipses there. And as well as demonstrating the capability of JWST to get these really exquisite phase curves of these kinds of planet, we did also learn some new things about the planet's atmosphere. So here now I'm showing the white light phase curve again with the transit and eclipses removed, compared to a grid of 3D general circulation models of the planet's atmosphere. And so we can learn a few things from this. First of all, the inferred temperatures on the day side and the night side of the planet are considerably lower than the planet's equilibrium temperature. And that tells us not only that the planet needs a layer of hazes, as we suspected, but that these have to be highly reflective hazes. And so a few different haze models can be used to fit this haze curve, ranging from these Titan-like Tholen hazes all the way up to some kind of arbitrarily maximally reflective haze with a single scattering albedo of 1. Also, in order to fit the amplitude of the phase curve, you need an atmosphere that is enriched in heavy elements. So you need at least 100 times solar metallicity or greater to get an amplitude that is close to matching the observed. So as well as this white light phase curve, we also have spectra. And so the emission spectrum, both the day side and the night side of the planet, shows evidence of absorption features. And using atmospheric retrievals, we find that water vapor is the most likely cause of both of these. However, we weren't sensitive enough to really distinguish the water abundance particularly well. So you can see in the posterior probability distribution for the water vapor mixing ratio, we're consistent either with a planet with hydrogen and helium and water all mixed in together in some proportions, all the way up to the edge of this probability distribution, which would be consistent with a 100% water steam atmosphere. And so one of the kind of trendy things that people are talking about with sub-Neptunes at the moment is this idea of water worlds, where you have a planet with maybe up to 50% water by mass, and then you could get some kind of steam atmosphere situation. It'll be very exciting, and in theory that's still consistent with this picture, as well as a metal-enriched but atmosphere that also consists of some hydrogen. On top of this, we also have the transmission spectrum, and we learned a little bit more about the composition as well. This places an even stricter lower bound. As I mentioned before, we need at least 100 times solar for the phase curve, twilight. For the transmission spectrum, we need at least 300 times solar metallicity in order to be efficient. We also get some constraints on the rate of haze production for these mixed atmospheres. But in the case of the steam atmosphere, we're still consistent with the transmission spectrum, so we still can't break this degeneracy between mixed envelope solution of a various different components or the steam atmosphere solution. So at this point, I wanted to turn to internal structure models to see if we can combine them with what we learned about the atmosphere and maybe start to answer some of these questions about what's the bulk composition of the planet? Is this kind of water world picture realistic? So first of all, just to introduce the internal structure models. So probably may have seen this kind of picture before. That's often been used to model sub-Neptune interiors of this kind of layered model, where you have an iron core, silicate mantle on top of that, some kind of water layer on top again, you have some hydrogen and helium envelope. And this has been used in the past to model sub-Neptune interiors, but we know that in reality it's not a particularly realistic. In fact, there are lots of different processes going on in the interior of the planet that might change this kind of picture. I've listed some of them here, including interactions between the core and the mantle and the envelope. And also, very important for this planet, at higher temperatures, we expect to see, rather than this distinct water layer with hydrogen and helium on top, it's much more likely that hydrogen, helium, and water are going to be miscible alongside any other volatiles present in the atmosphere. So rather than having this kind of two separate layers, you have this big mixed envelope of all the different chemical species. And so in general, I refer to the envelope as this entire gaseous layer for the planet, where the atmosphere is just the upper portion of that, so pressure is less than around 100 bar. And this mixed consideration obviously depends on the temperature and pressure regime that you're in. But for GJ1214b, if we compare it to the water phase diagram, the atmospheric temperatures and pressures of this planet place any water firmly in the vapor phase. You would definitely be in a sort of mixed envelope scenario rather than a layered hydrogen and helium over water. So these are the internal structure models. So the process for connecting this to the atmosphere looks something like this. So we start off by taking a grid of self-consistent atmospheric models that are consistent with what we've observed. Then using basically the atmospheric chemistry and the temperature profile from those models as boundary conditions, we can then generate internal structure models with our envelopes, extending that temperature profile down into the interior and maintaining the composition. And then we can compare those interior models to the measured mass and radius of the planet to try and place constraints on the bulk composition. So that's what I've done for GJ1214b. So first of all, looking at the atmospheric models that we generated, so considered a range of different compositions and haze production rates that are consistent with the emission spectrum of the planet here. So I divided these sort of into two categories. So the mixed atmosphere scenario, where a number of different compositions can still be consistent with the observations, and then also the pure water atmosphere case on the other side. And you can see the impact that changing the composition and changing the haze production rates has on the temperature profile. For the mixed atmosphere case, it turned out that one particular haze production rate in our model grid provided a better fit, this 10 to minus 11. And whereas for the water vapor atmosphere, you can actually vary the haze production rate quite a bit and still be consistent with. So this is the range of models that I used as input to the internal structure, generated mass radius relations, and tried to see what's consistent with. Unfortunately, when you try and fit the interior of any object, just a mass and radius, this problem is fundamentally different. So you can always just, if you increase atmospheric metallicity, you make the envelope denser. So that means the planet radius shrinks, but then you can just increase the total envelope mass fraction and decrease the amount of rock such that you match the mass and radius again. Which means that for any given atmospheric composition, you can find some envelope mass fraction that's going to be consistent with the mass and radius of the planet. But there's still some information that we can get from this. First of all, talking about that 50% water world, you can see that that's kind of way off the mark, the radius. You need a much higher H2O mass fraction in order to get that scenario. I'll come back to that one later. And then for these mixed envelopes, you can see that the total envelope mass fraction varies pretty strongly with. So rather than just looking at a couple of different models that are consistent, I explore the full range of different atmospheric compositions. So here shown as a function of atmospheric metallicity or correspondingly mean molecular weight of the envelope. And you can see how the bulk mass fractions of hydrogen and helium and of the total envelope change pretty considerably as you change the atmospheric composition of the planet. Now the bulk H2O fraction here, now this is for the mixed atmosphere, so we have hydrogen, helium, and water all mixed in. I would say that the bulk H2O fraction should be taken with a bit of a grain of salt because there could be additional water partition in the core, but that shouldn't affect the hydrogen helium mass fraction for the planet too much. So if you look at the right-hand panel, I've just zoomed in on the hydrogen helium fraction. And we see that when we account for all the different constraints that we get from the emission spectrum and the transmission spectrum, that the best fitting hydrogen helium mass fractions range somewhere between 2 and 6% for the planet. And what I think is really interesting about this is that the inferred bulk fraction depends really strongly on the atmospheric composition of the planet, as well as the haze properties. And so for GJ1214b, right, it's still quite difficult. We're still only getting a lower limit. But potentially for other sub-Neptunes, we're starting to see very tight atmospheric constraints on the mean molecular weight of that. And so for other planets, we might be able to get really precise measurements of the hydrogen and helium. But for now, with GJ1214b, we're limited. Also, better understanding of how hazes work in sub-Neptunes might help us find even further. So these were the mixed atmosphere solutions, but as I said, there's also this idea of the water world steam atmosphere scenario for this planet. And so I also ran those models to see what the required H2O mass fraction would need to be in order to fit the mass and radius. And as I mentioned, the steam atmosphere you can fit with a number of different haze production rates. So I tried generating these models for different haze production rates that are consistent with the atmosphere. And the finding was that even if you decrease the haze production rate as much as possible, that gives you the hottest possible atmosphere. And that means that your steam atmosphere is the lowest density that it can be, and therefore you need the smallest water mass fraction in order to fit the mass and radius. So even in that case, of that low haze production rate, you still need something close to 80% biomass. I'm not really a planet formation expert, but I've talked to people about this, and I think it's very, very difficult to form a planet with that much water, with that much ice. You need an ice to rock ratio of something like, I think 3.76 to 1 or greater, which is just like a bit nuts. So I think from this, you're able to disfavor this water world solution for the planet, but you need to look at both the atmospheric information and the interior in order to do this. So I'll just leave my summary up here and take any questions.
All right. Thank you, Matthew, so much. Any questions from the audience? Yeah. Nestor?
Thank you, Nestor Espinosa, Space Telescope. This is fantastic stuff. Given these constraints that you're having here, what would be your prediction into what is the next step for GJ1214? We all know what it is made of, right? So what is the next observation, perhaps, that you're predicting from these constraints should be made?
Yeah, that's a very good question. So I know there are other observations that haven't been published yet, but I think it would be really interesting. I'm not sure what exactly they're finding, but I think it'd be really interesting to see if people are getting if we could actually pick out there, because that should be a pretty so I think that could be a really interesting one. Yeah, I mean it's always going to be a challenging target though for that.
Thank you. Another question from Eric, I think.
Hi, Eric Lopez, NASA Goddard again. Fantastic talk. I'm curious about I agree with everything you said about the steam world scenario. I'm wondering, the Tholen hazes that you talked about in that scenario as well. Have you thought about how the chemistry would work? I mean, in practice, steam, it doesn't mean actually 100.00%, but in a water-dominated context, make those Tholen hazes?
Yeah, that's a really good question. I do not know. I don't think we really understand how you would produce these kind of hazes on that kind of atmosphere, so that's still up for definitely interesting to look at, given that we.
Okay, time for one more quick question. Yeah, Josh.
Great talk, Matt. My question's in regards to the context with other planets like TOI270d and K218b. How do you think this fits in the context? Do we have like a unified theory for sub-Neptune interiors?
Yeah, excellent question. So TOI270d, I think, based on, they got much more precise constraints on the beam of the atmosphere. And they were able to do a similar kind of analysis to this. And they find a pretty similar looking picture, right? There's like a few percent hydrogen helium, but it's in volatiles, maybe 94 mass fraction. But I think TOI270d and GH1214b appear to be quite similar in terms of internal structure. K218b a little bit trickier because it's colder. Interpretation where the hydrogen and the inside, or maybe it's in liquid phase. So I think it's a little bit trickier with that because of the temperature. Yeah, the other two I think seem to be pretty.
All right, any other questions? No. Okay, let's thank one more again. Matthew. Okay, now it's time for the next session of lightning talk. So I would invite actually everyone who is going to give a talk to probably move somewhere here for the interest of time. So when you see your slide, just come and talk, and we have 2 minutes for that. Also, this is for names between O and Z.
O to Z, yeah. Everybody who hasn't gone yet. This is the last line we've got. Awesome.
Hi everyone. Can you hear me? Yes. I'm Natalie. Sorry. Can you hear me? Okay. I am Natalia Oliveros. I am a graduate student here in Johns Hopkins, and about this incredible method to detect, to identify brand dwarf candidate variables. This is very interesting because it's concerned to all of us understand the internal structure of the atmospheres of brand dwarf and exoplanets. And with this method, we use only one near infrared spectrum to determine, using spectral indices, if one brand dwarf is variable or not, it's candidate variable. And basically, we study the details that what parts of the spectra change in time more than the others. And with that, we compare some indices and we obtain the answer about their variability. So you want to know more about the method, it's available also in GitHub, and if you want to talk about spectral indices, atmospheres, and variability.
Okay, next one.
Aki's, but I don't think she's here.
What?
Yeah.
Okay, so
So don't forget about HWO.
So what is it? Habitable Worlds Observatory, NASA's next flagship mission concept recommended by Astro 2020 Decadal Survey, and some nice pictures and orbits.
That's the design that has been.
So you can take a picture probably and read the details.
Direct imaging is the future.
So expected launch in early 2040s. Oh my gosh, that's long way. Next one is Jacobo Terrani. Do we have? There's the map. Yeah, it's on.
It's on. Okay. Can you hear me? Yeah. So I'm Jacopo Terragni, and I work at Goddard. I'm an MPP in the Auto Environments Lab. The lead of the lab is Erika Kohler. And what we do there is try to measure fundamental properties of materials at very high temperature and high pressures. So it's like kind of difficult because like in all of your papers, I guess at the bottom there's something like, oh, we really need more additional lab data on this topic. Or like, yeah. And the reason why there are no such data is because, yeah, they are not like easy to measure. Like materials tends to, and lab equipment tends to break when you go to such high temperature and pressure. So as I said to like my colleagues at Goddard, if you see me running out of the building, run with me because like it's a good idea. So actually we have right now like 3 different projects. Like we're trying to measure optical properties of atmospheric particles at high temperatures. We are trying to measuring saturated vapor pressures up to 2400 Celsius of refractory materials, like for example, silicate clouds that were mentioning before. This is kind of measurement that we are trying to do. And this is our last project that we are doing with Vincent Kaufman, Geronimo Villanueva, and Sara Faggi. We are mixing like lab and computational modeling, but the thing that you see here is like an example of collision-induced absorption measurements at high temperature and high pressures, and the 2 things combined together. So I think this is particularly relevant for all the modelings that you're doing. So if you're interested in like to update your database of data that you're using in your models, I'm here if you want to talk about it. Thank you.
Okay. Thank you, Jacopo. Jacopo, right? Okay, next one. I don't see a name here. Oh, in the bottom. Noah. Okay. Here's your mic. Okay. So just talk to me.
Hello, could people hear me? So I'm Noah Tusho, and I'll be talking today about my work on the HPIC, the Habitable Worlds Observatory Preliminary Input Catalog. I'm an NPP at NASA Goddard, and I work with Chris Stark, and also this work was also working with Eric Mamajek at the EXOP office. And so this is highlighting a very early preliminary input catalog for HWO, a list of target stars that is used as an input for yield calculations and potentially other trade studies. And so it's a list of around 13,000 bright nearby stars, which are potential direct imaging targets. And we've gathered astrophysical properties and photometry for each one. And we construct this catalog using an automated pipeline that's easily updatable. So it's currently constructed using the test input catalog and Gaia DR3 using a bunch of selections based off of distance and magnitude. And we think that this catalog will be useful as an input for future HWO trade studies and yield calculations. And it's currently publicly available on the NASA Exoplanet archive, which you can see down there. So if you're interested in potential input catalogs for HWO, come talk to me. Okay, thank you.
Thank you, Noah. Okay, Amy Tucson.
So hi everyone, my name is Amy Tucson and I'm a new postdoc at NASA Goddard. So I just finished up my PhD at the University of Cambridge, and that is the left-hand side here. So during my PhD, I was working on uncovering long-period transiting exoplanets with TESS and CHEOPS. So very briefly, I made a pipeline to discover the observational signatures of these long-period planets in TESS data. And these are what we call duotransits, which is the top plot over here. So we have these two transits separated by a long gap. And then because of that, we don't know the orbital period, but we know it has to be one of a set of values, like you can see on the right-hand side. I would then use the CHEOPS telescope to follow up these different period aliases to try and figure out which one is the correct orbital period. So you can see that at the bottom here, you know, the first observation we made, well, there should have been a transit there for X and Y period alias, but it was a flat line, so we can rule those ones out. And then the second observation we got, we see a transit. So we know that that is the true period of this object. So the overall result of that work was I found 5 long period planets with the pipeline that then had their periods recovered by CHEOPS, which was really great. So now, in my new position, I'm really excited to start working on extracting and analyzing TESS light curves for asteroids. So for this work, I'll be working with the TESS full-frame images, developing a pipeline to extract their light curves, and then analyzing them to get properties like their rotation periods. So although this might look like, you know, confetti streamers across a TESS image, it's actually like the trails of the asteroids that have been observed during this sector. So we're going to have lots and lots of asteroid light curves coming soon. So yeah, please come chat to me, anything data analysis, pipeline development, exoplanets, asteroids. Thank you.
Thank you, Amy. Next one, Nicole Wallach.
Hello everyone, I'm Nicole Wallach. I'm a postdoc at Carnegie EPL, and I'm primarily interested in using ground-based and space-based observatories to study exoplanet and brown dwarf atmospheres. I also observe and model directly imaged protoplanetary disks. So here I'm showing some figures from 2 different recently accepted papers. On the left, I'm showing results from the COMPASS survey. So COMPASS is the largest JWST program awarded to date dedicated to exoplanets. So here I'm actually showing results from the first observation that were taken with the COMPASS as part of the COMPASS sample. So here is a sub-Neptune, one of 12 super-Earths and sub-Neptunes that we're looking at as part of our program. So on the right-hand side, I'm showing results from a survey of protoplanetary disks that I led using the Vortex coronagraph on Keck. So we looked at 43 different protoplanetary disks that all showed substructure at ALMA wavelengths, and we were looking at L prime to see if we could directly detect any planets embedded in those protoplanetary disks that could be driving that substructure. We did not detect any new planets, but we were able to place fairly robust constraints on the masses of planets that could be in those substructure driving systems. So on the right-hand side, on the far right, I show our overall survey sensitivity of these 43 different disks. Please chat with me about direct imaging or JWST observations of small planets, or sort of anything else. Thank you.
Thank you, Nicole. And that's it. That's the end of this session. We go in a coffee break and we reconvene at 3:15 p.m. Thank you, everyone, and let's thank once more all the speakers from this session.